Okay, so last week, 2 weeks ago, the last lecture, we studied the interplanetary environment of space weather created by the sun. We really weren't considering any planetary interactions in that particular lecture. This week, we're going to study the interactions with one planet in particular, the Earth. Thus the title of the lecture, Terrestrial Responses. And we'll get into some of the technological impacts. As you'll see next week, well, just to go through the outline formally, we'll start by talking about the Earth's magnetic field and what that means in terms of creating a magnetosphere, radiation belts. We'll then talk about what I call the mesosphere, ionosphere, thermosphere system, or MIT system. That sort of rolls off the tongue better than ionosphere, thermosphere, mesosphere system, which you'll sometimes see, or ITM. Anyway, that's the upper atmosphere of the Earth and how that interacts with the interplanetary environment to give us some space weather effects. And then we'll get into the details of what those effects are, specifically here at Earth. But we're only going to talk today about UV and X-ray irradiance from background active regions and solar flares, as you saw 2 weeks ago. The sun is continually putting out UV in the form of from active region heating, but there are also flares from the solar magnetic eruptions. We'll talk about the impacts of those two sort of photonic space weather effects. And then we'll also talk about how the solar wind can trigger minor to medium geomagnetic storms. We'll talk about what a geomagnetic storm is. And we'll talk about some of the technological impacts of both of those as well. But I'm going to say for next week, the big impacts from the CME and SEP events that can accompany magnetic eruptions, because I just couldn't fit that into one lecture here. So next week, we'll talk about the more extreme events, some historical extreme events, and the technological impacts thereof. So launching right in. Okay, first of all, the Earth has a magnetic field, as we all know. I'm not going to spend too much time on these slides. There's a lot of detail here. For the record, you can go through them later. But we all know it's basically a north-south bar magnet, dipolar type magnetic field. It does have this funny thing called the South Atlantic anomaly off the coast of South America that will come into play in next week's lecture, in particular when we talk about charged particle impacts. But very quickly, when we talk about the Earth's magnetic field, we talk about the geomagnetic field vectors in terms of the horizontal field, shown here as H. That's composed of the north and east horizontal vectors. And then the BZ, or the downward vector for a geomagnetic field, together with the horizontal field, forms the full magnetic field vector, whose magnitude is denoted by F. So you'll sometimes see these funny things for H, D, Z, and F in terms of magnetic fields on the Earth. H is horizontal, D is the declination angle, the angle away from the north, and F is again the magnitude. So just keep those in mind as you see some of the plots later. This slide I'm not going to go over at all. It's very complicated, but it just points out that there's lots of different ways to orient the magnetic field of the Earth and space. And this is a really nice video produced by the NASA Science Visualization Studios at Goddard, comparing all of these different geospace coordinate systems that can be used to describe, again, magnetic fields and directionalities in the Earth. So I'm not going to go into too much detail. It would take too long to go through all of these, but you have the reference there, and it's well worth watching, both reading the slide before it and watching this one to see how all of these different coordinate systems interact. So the meat of the problem here is, though, that we have a magnetic field around the Earth. It's nominally a dipole magnetic field in space, but now you put it into the solar wind environment caused by the sun, as we saw last week, and you get a very different beast. And in particular, this shows the sort of overall structure of what's called the magnetosphere, which is the sort of the shell around the Earth, the magnetic shell around the Earth, that's shaped by the magnetic solar wind. So in the far left here, we see the incoming solar wind with basically planar fields of magnetic field, because again, recall the scale. The Earth is very, very small compared to any magnetic solar wind or CME structures coming from the sun. And so basically we have the planar fields coming in. However, because it's a supersonic system, it goes through a bow shock when it encounters the magnetic density of the Earth, of the Earth's field. And then it reconnects, as shown here, with the Earth's magnetic field. And keep in mind that what I'm showing here is the ecliptic plane. That's the sun-Earth line. So you see the noon and midnight sectors of the Earth. But the magnetic field, as shown in the earlier slides, is tilted with respect to the rotation axis of the Earth. So the magnetic field of the Earth is actually kind of wobbling around the rotation axis during the day-night cycle. And so this entire structure is actually a 3D structure which wobbles on a 24-hour period. But the main thing to keep in mind is it's swept back into a very elongated structure with what we call the magnetotail back here. So again, if it were just a dipole field, it would be these nice dipolar elliptical structures. Instead, we have this extremely drawn out magnetotail structure, which will play into how this interacts with the solar wind to cause space weather and geomagnetic storms. So this is a movie showing kind of the basic, it's not completely accurate. You notice that the magnetic field is not quite accurate compared to the rotation.
Something strange happens. An invisible shield.
You turn off the sound and you can see that the diagram here is of solar wind magnetic field coming in, reconnecting with the front side of the Earth's dipolar field to wrap around and create that magnetotail structure we saw earlier. And then the magnetotail itself undergoes reconnection in the far tail. And when it does so, it snaps back to create what's called a dipolarization event, creating a more dipolar-like field. And they're illustrating here with these clouds of particles, acceleration of particles due to that magnetic reconnection. So much like a solar flare magnetic reconnection, when that reconnection occurs, you can accelerate energetic particles trapped along those field lines back towards what in this case becomes the polar regions of the Earth. So that's kind of the dynamics of the magnetic tail of the Earth. This is a more detailed look at the actual sort of magnetohydrodynamics that takes place in the magnetospheric structure of the Earth. This is a model, but what it shows is that in addition to just these simple snap reconnections, you actually have quite intricate interactions between, in this case, what was a minor CME front and the plasma trapped in the magnetosphere itself. So you can see there's very detailed Kelvin-Helmholtz instabilities along here. And here come these snapping back bursty bulk flows, as they're called, bringing plasma backwards from the tail region into the polar region. This is actually looking straight down on the Earth. So noon is here, midnight is here. But this is all coming, you have to imagine this as a 3D volume. And this is the particles coming back into the inner magnetosphere from the tail region in what we call these bursty bulk flows, for lack of a better term. And again, these result in dipolarization of the field. Now, that doesn't mean depolarization, it means dipolarization. The field kind of snaps back into a more dipole-like field. It's a funny term, but you will hear that a lot from magnetospheric people. When there's a big event, there's a dipolarization, and that means there's lots of accelerating particles being thrown back into the polar regions. So the takeaway is that the magnetic field is constantly changing. There's this magnetosheath boundary with instabilities through interactions with the interplanetary magnetic field, which we call the IMF, or could be in the solar wind, or it could be a CME bringing magnetic field into the system here. So what happens when you have a changing magnetic field in time? We know from Faraday's law that induces electrical fields. And electric fields, when you have a charged plasma environment like you do trapped around inside the magnetosphere, that induces electric currents. And this is a very complicated diagram showing, again, the magnetosphere, kind of the magnetopause, the tail region, and all the kinds of currents that can occur in the system due to the changing magnetic field as the solar wind constantly kind of waxes and wanes, or a CME comes through with a big front and causes a major change in the configuration of the magnetospheric field. Two big ones to keep in mind here that are very space weather relevant are a ring current. This is electrons going this way and ions going the other way towards the, or is it the other way around? I always forget. But anyway, ions and electrons are separated as they come back from the tail, and they travel around in this direction, this meridional direction, to form what's called the ring current. There's also these field-aligned currents which go along the polar fields of the Earth to funnel, as we saw in the movie, charged particles down into the polar regions, which, surprise, cause the aurora. So that's why the auroral oval is basically defined by where the field-aligned currents are anchoring in that system. There's other cross-tail currents and night-side currents that don't really make too much difference in terms of direct space weather effects. There's also the day-side magnetopause current. But the ring current is very key, and the field-aligned currents, which cause the aurora, are two key sources of current in this system. So, you know, as mentioned, it's not just that there's empty space out there and magnetic fields, otherwise there'd be very few dynamics. It's actually a plasma-filled environment. The source of the plasma is the ionosphere itself. We'll talk about the ionosphere in a little bit. But the ionized elements from the ionosphere actually diffuse outward and populate this, what's called the plasmasphere, around the Earth. And this is to scale, so it's only a few Earth radii out that the plasmasphere kind of concentrates. And the ring current, which is hard to see, is kind of a blue, hazy thing, a little on the edge of the plasmasphere. But you can also see these two interesting green rings around the magnetospheric equatorial system. And those are the Van Allen radiation belts. And those are not just sort of thermal plasmas leaking up from the ionosphere. Those are highly energized electrons and protons trapped within the magnetic field system of the magnetosphere. So we call this whole system, where there's plasma around the sort of, you know, from 1 to 6 or 7 radii, Earth radii out, we call that the inner magnetosphere. The outer magnetosphere would be the tail region or the magnetopause in the front. So looking a little closer at the Van Allen radiation belts, these were discovered in 1958 during the first satellite that we orbited, Explorer 1. Principal investigator was James Van Allen, thus we call them Van Allen belts. And it wasn't Van Allen, but one of the members of his team was quoted at the time when they saw the Geiger counter traces from the mission as saying, "My God, space is radioactive," because these charged particles are very high energy that are trapped in the radiation belts. And there's basically two belts. We talk about the inner belt, which is anywhere from 1,000 to 8,000 miles, which is more like 7,000 to 12,000 kilometers, or 1.2 to 2 Earth radii. This is predominantly protons caused by spallation from cosmic rays coming in through the plasmasphere and the atmosphere. So it's mostly protons on the inner belt. Note that the low Earth orbit is below, almost entirely below the proton belt. Then there's the outer belt here, which is much larger and goes from about 3 RE out to about maybe 10 RE. It's predominantly electrons from anywhere from 0.1 to 10 MeV, which is highly relativistic and therefore highly penetrative. And you can see that encompasses both the GPS satellites in medium Earth orbit, and it goes all the way out to geo orbit, where we have our weather satellites and other communication satellites. So the outer Van Allen radiation belt, composed primarily of high energy electrons, is the one that has the most effect on satellite systems. We'll talk more about that next week. This is just an outline of how this system works right now. One thing, I won't spend a lot of time on this, but you'll hear people when they talk about the radiation belts talking about the L shell. And the L shell is really just a number that denotes the magnetic field line. When you're going on the magnetic equator, it's along the radius of the Earth, essentially. It's equal to the radius of the Earth outside of along the magnetic equator. But these lines follow in to the polar regions. So in the polar regions, you can go through many L shells very quickly. And you'll see plots later of the L shell electron flux. So this is just yet another coordinate system to be aware of in use in magnetospheric physics. And the question that came up as soon as they started measuring a lot of these high energy electrons and protons in the radiation belts is, where are these things coming from? And for a long time, it was sort of posited that, well, they were coming in from outer space, from the interplanetary medium pushed by the solar wind, but that's not quite how it works. The solar wind actually, particularly when you get a very large event like a CME, will actually deplete the radiation belts, because it, as a fluid front coming through, it'll actually sweep out a lot of the particles, scattering a lot of the particles out of the belts, as we'll see in a bit. And so they noticed that this would happen. The solar wind would actually deplete the radiation belts, and then they would refill over time. And they found that it's really two mechanisms of wave fields of the magnetic field that are accelerating the particles back to these high energies in the Van Allen radiation belts. So the chorus waves, as they're called, and I won't go into detail about the frequencies and things of these waves, they're essentially magnetic field waves taking place in the inner magnetosphere, accelerate the electrons back up to relativistic energies, and as they bounce back and forth between the polar regions due to magnetic mirroring. And then His waves, which have a different profile and frequency, actually can scatter the electrons. So these two wave mechanisms are competing constantly to create the radiation belts. And the balance is that we have a sort of a relatively static two-belt system, although it can get more complicated in big storms. So here's one of these complicated plots. This is on the y-axis, the L shell. So think of this as sort of distance away from the Earth along the equator, or in the polar regions, coming down into the polar regions. And along the x-axis is the date from 2012 until 2015. So 3 years of electron flux data. These electrons are 4.2 MeV, so they're highly relativistic. That'll, for instance, go straight through any MLI coating on a spacecraft. It'll go straight through thin aluminum shielding and bury itself in your electronics. And you can see here that there are these occasions where there's big dropouts of the field, followed by strong flux enhancements across many L shells. These are CMEs coming in and essentially sweeping out the the charged particles of the radiation belts, and then the geomagnetic storm and the wave mechanisms subsequently filling the belts back up, at least the outer belt. You don't see the inner belt on this because it's just electrons. But you can see almost everywhere you have a major filling, there's first a depletion. So some of these smaller events might be solar wind events that come through and deplete the radiation belts before they're refilled. Then there was a long quiet period in 2013-14. And then here's a very large storm, well-known one, the St. Patrick's Day, March 27th, 2015 storm, where again, you see a prompt emptying of the belts followed by a re-energization. Something else to notice is there seems to be like a hard floor at sort of 3 Earth radii, or L3, L shell 3, at which these electrons don't penetrate. And that was a big mystery for a while, but it again has to do with the wave fields and the scattering of those particular electron energies. So this is a movie of taken by the Van Allen probe's mission, which was a NASA mission with 2 satellites in a highly elliptical orbit going through the outer radiation belt. So this is an electron telescope that's, again, just looking at electrons, again, just looking at 4.2 MeV electrons, and it's over 2 years. So you'll see as the orbits process around the Earth, there's a very large variation in the flux, which is the color coding here, of electrons measured in the belt. And I won't show the whole 2 years. This is just to give you a feel for what the fluctuations look like as the solar wind is continually changing the magnetic field of the Earth, leading to differing scattering and electron acceleration mechanisms. And there was the large storm from St. Patrick's Day. And one thing to keep in mind is this azimuthally symmetric structure is just assumed. They only have data along these orbits, but they made this very nice, completely symmetric plot, which is not real. We know that this is not a symmetric system because, as you see from looking at the magnetospheric structure, it's highly shaped and highly dynamic as the solar wind messes with it. So this is really not something to take away as what the radiation belts really look like. It's just kind of trying to give you a feel for how big they are and the flux changes that occur over time. Now let's move a little farther down into the upper atmosphere and see what the effects of interacting with the interplanetary environment are in this range. So the thing about the Earth that's really interesting for space weather, it has both a magnetic field and an atmosphere. Every planet in the solar system has a different space weather profile because they don't all have atmospheres and or they don't all have magnetic fields. For instance, Mercury has a strong magnetic field, but no atmosphere. Mars has a somewhat of an atmosphere, but no magnetic field to speak of. So there's lots of different variations here. Earth is interesting because it has both a very thick atmosphere and a magnetic field, a very strong magnetic field. So looking at the atmospheric layers that are relevant to space weather really starts with the stratosphere at an altitude of 50 to going from top down, 50 to about 16 kilometers. This is sort of the top layer of the troposphere where all the weather happens, where we live. Above that is the mesosphere and the thermosphere. And the ionosphere is really just this whole thing, mesosphere, thermosphere, ionized. And how does it get ionized? Well, it gets ionized by X-rays, extreme ultraviolet, far ultraviolet, middle and near ultraviolet radiation coming from the sun. So you can see this is a plot showing where these energetic photons are kind of stopped in the system. X-rays tend to make it almost all the way down to the stratosphere, but the extreme ultraviolet and far ultraviolet, also the middle UV, are really the ones responsible for creating this ionospheric density plot, which is shown here. So as you go up in altitude, the density drops, but the constituent species also change, and the electron density rather, increases concomitantly. And we talk about the three layers of the ionosphere, the D, E, and F layers. Those don't always exist. It's a very dynamic system, but they're caused by, again, this constant EUV flux coming in from the sun. And then when we get X-rays from solar flares, we get enhancements, as we'll see. So, whoops, wrong way. So the mesosphere is that middle, literally the middle sphere, from about 100 down to 50. And then the thermosphere sits on top of that. It goes anywhere from 1,000 down to about 100. And outside of that, we talk about the exosphere, where there's actually atmospheric escape occurring in the atmosphere. And you can see here the temperature. The reason this is called the thermosphere is because suddenly the temperature jumps dramatically up to 800 in solar minimum periods to 1,200 in solar maximum periods. So what's going on there? Well, that has to do with the variation, as we saw, as the sun goes through its cycle, that the EUV radiation from the sun is also changing dramatically. So during solar maximum, the thermosphere is actually about 50% hotter than it is on average in solar minimum. And we'll talk about the consequences for that for technology in a bit. So this is another plot of energy deposition, D, as a function of altitude and wavelength. Wavelength in this case is on the x-axis, so that we're looking in the deep and extreme ultraviolet here. For instance, here's the helium-2 304 angstrom line in the sun, and there's a lot of energy deposition just due to this one line, all the way down to about 100 kilometers. So this is a very interesting plot showing kind of both altitude variation and then coronal EUV and distinct spectral line radiation from the sun, creating our ionosphere. And these are altitude plots of that same thing, basically. On the left, you see the ionization profile. On the right, you see the molecular dissociation profiles. The top row is during noon, and the bottom row is during sunset. So when the sun is directly overhead, it's beating down and doing a lot of ionization and dissociation, all the way down to about 100 kilometers. When the sun sets, begins to set anyway, these profiles rise up and become somewhat smaller in magnitude. So this is basically the shape of the ionosphere, which varies dramatically with the sun as the sun goes overhead of different parts of the atmosphere. And bringing in the technology now a little bit, what does the ionosphere give us? Well, it gives us a reflective layer for radio communications. So you'll see, you'll hear people talk about skywave communication with radio. What that means, in ham radio lingo is they're using radio waves that have been reflected from the sky and coming back down. So if you want to have long distance communication, you're going to use the ionosphere, typically, and more like the F1 and F2 layers actually. This is a diagram showing that sometimes the E layer gets a little intense and you can actually bounce off the E layer, not just the F layers. But in any case, it's all kind of the same mechanism. It's radio waves driving electrons in the ionosphere to re-radiate the wave downward and create over the horizon communications. There's something called the maximum usable frequency, which is due to the density of the ionosphere. I won't go into too much detail, but it depends on the angle you're trying to get to and the density of the ionosphere. So you can see that depending on the changes in the ionospheric density we saw earlier, you're going to get different radio frequencies that reflect at different layers and therefore go different distances. So the ionosphere completely controls both radar and radio communication in the Earth. So, and then this just points out that radio frequencies higher than the maximum frequency go straight out to space. So if you want to talk to somebody in space, you've got to use very high frequencies that don't resonate with the ionosphere, and you can talk to the space station. Okay, so this is another plot showing what happens between the sun-illuminated atmosphere and the nighttime atmosphere. During the daytime, we have the D layer, the E layer, F1 and F2 layers at these various altitudes shown here. At night, that all contracts down into one single layer of E layer and a little bit of a top layer, a topside F layer. So the ionosphere itself, the ionization profile is very dynamic just with the day-night cycle. And that's something to keep in mind when you talk about the various layers and also radio communication, you can see is a little bit more complicated during the day side periods. And I would be remiss if I didn't talk about how the lower atmosphere actually couples up with the upper atmosphere to create what is sometimes called space weather from below. It's nothing like the big space weather we get from the solar storms, but there is sort of a priming or a conditioning of the upper atmosphere, if you will, by various mechanisms coming up from the tropopause. For instance, mountain waves, as the winds go over the large mountains, they will generate waves that will actually propagate upwards and can get into the mesospheric and even thermospheric altitudes. Secondary gravity waves can cause traveling ionospheric disturbances, which will, in other words, these ionospheric fronts will move with these waves. There's breaking gravity waves from, again, thunderstorms, and then plasma bubbles, which are the Rayleigh-Taylor instability, as we'll talk about in a bit, caused by density perturbations on the bottom side of the mesosphere. And then you've also got these energetic particle precipitation events coming in from the auroral field-aligned currents, for instance. There's daily tides as the atmosphere swells up and down. And then the polar vortex is actually linked to some of these large-scale mesospheric flows as well. So as I mentioned, the gravity waves can go up and actually start to trigger Rayleigh-Taylor instabilities, which is that instability when you have a denser fluid on top of a lighter fluid. You get these fingering instabilities. The magnetic field here comes into play, and so we call it a magnetic Rayleigh-Taylor instability. But you'll hear the term spread F for the fact that these sort of density bubbles that suddenly burst up from below will cause interference with radio signals trying to come down, for instance, from GPS satellites in middle Earth orbit. You'll get what's called GPS scintillation due to these bubbles. We'll show that in a bit here. And then also these TIDs will cause scintillation and difficulty with radio communications in the polar regions in particular. So in summary, the drivers of the MIT system are really the sun, the irradiance from the EUV background and from flares, the solar wind and transients, which drive the magnetosphere, as we saw earlier, to create these electrical fields in the magnetosphere itself, but also the upper atmosphere, upward propagating waves and tides, all play into how this system reacts at any given time. So these are the big constantly changing things over here. This is more of the, slower changing, almost constant background conditioning of the system, which determines how it reacts during large changes. due to the solar inputs. And we've gotten pretty good at modeling these things. This is the in-car whole atmosphere community model extended up to 700 kilometers and including chemistry and ionospheric ionization, of course. And if I play the movie, you can see how the day-night cycle is very obvious. There's really this high ionization on the day side, not much on the night side. Another thing interesting to note here, though, is there's always these sort of two bands of ionization around the magnetic equator. And what's going on there? What's going on there is called the equatorial ionospheric anomaly, or EIA, sometimes also called the Appleton anomaly, after the person who discovered it and won the Nobel Prize in 1947 for the discovery. It's basically an upwelling of plasma at the magnetic equator, and as that upwelling occurs underneath this nearly horizontal magnetic field spanning across the equator, it sort of forces the particles to travel along the field in these two different directions. And so you get this sort of buildup of plasma in these two big bumps, as shown here. And I think it transitions to show us a horizontal view. Yeah, there we go. So there are the two bands that you'll often see in ionospheric plots of the Earth's upper atmosphere, along with the magnetic field lines, which are predominantly horizontal here in the magnetic equatorial region. And that has a lot to do with why the plasma bubbles and magnetic Rayleigh-Taylor instability occur mostly here along the equatorial regions. So as I mentioned, we call this sometimes space weather from below, because it's not really driven so much by the sun, it's driven by the day-night cycle and the upwelling of ionospheric plasma as the day-night cycle occurs. And what happens with these, and particularly with these scintillation bubbles, as they're called, is that when, again, as I mentioned, when you have GPS satellites you're trying to lock onto with a receiver on the ground here, and typically you need about 6 to get a very good position. If these are transmitting through these very large ionospheric bubbles, the signals are going to get scrambled, essentially. So we talk about the variation in total electron content, or TEC. TEC is kind of what you'll hear as the coin of the realm in ionospheric and GPS communications in particular, and GPS navigation in particular. So the total electron content of the ionosphere, in a perfect ionosphere, would be completely smooth all the time, and you wouldn't have to worry about it in terms of communication or GPS. But it's not, the reality is it's not smooth all the time, and you get things like big scintillation bubbles occurring, which can scramble the signal from GPS systems. So the big bane of GPS is scintillation. It's caused both by these Rayleigh-Taylor instabilities and by the energetic particles in the polar regions kicking off the TIDs we talked about earlier. This, for instance, is an illustration of where the swarm satellite, which is orbiting in low Earth orbit, loses lock on GPS occasionally. This is a heat map of the occurrences over a period of time in which that satellite was not able to lock onto GPS at all. You can see most of the occurrences are along the magnetic equator here and here, but a good number of them are also down here in the polar regions, which are due to those traveling ionospheric disturbances. Again, we'll see a good example of a TID effect next week when we talk about a big geomagnetic storm, which tends to generate TIDs very efficiently. So move that. Okay, so here is an actual illustration, an actual observation image of the night side ionosphere, looking again at these equatorial anomalies here, ionospheric anomalies, but also showing the bubbles that are occurring along the magnetic field lines due to this density inversion that takes place at night. So these large bubbles here are the spread F Rayleigh-Taylor bubbles in the ionosphere. And these are, if you were to try to use GPS right below this, for instance, this is South America. It's too obvious. But if you were in the Brazilian Amazon trying to use GPS right now underneath one of these systems, you would not likely be able to get lock. These are fairly serious scintillation sources. And you can see they travel along the equator and cause these very large depletions in the ionosphere. And they're also quite turbulent. So everywhere you see these depletions, you're going to get turbulence that causes GPS scintillation. Now, this is fitting everything on one slide. And I never recommend this kind of slide, but I have to show it to you because it's so common in the MIT science field. It's shown at almost any conference you'll go to on ionospheric, thermospheric physics. And it does capture all of the dynamics we've talked about, and even some we haven't. We didn't talk, for instance, about these polar cap convection cells that start up during geomagnetic storms. We didn't talk much about the solar-driven tides, but it's all here. And I don't recommend, again, doing this. If I wanted to really talk to all of this, it would take 15 minutes. I'm not going to do that. So I really recommend not including slides like this in your talks. And in fact, as a quick interlude, I do recommend checking out this talk by Patrick Wilson from MIT called "How to Speak." He's he passed away, unfortunately, a couple of years ago, but he was an excellent speaker. He was an AI researcher from MIT, and he started giving this course on how to give a technical talk some years ago, and it's become kind of, in my opinion, one of the most important videos for career advancements that have ever been made. I really recommend watching it because even this talk I'm giving, I've recognized many times when I violated some of his cardinal rules for how to communicate most efficiently when you're trying, particularly using PowerPoint and slides. And it all comes down to reducing clutter and getting your message across clearly. So that slide, when I put that slide in the talk, and I thought, oh no, I'm including this slide that I always hate to see in a talk, because you'll see people put that slide up and try to talk to it within 30 seconds. And it's just, there's way too much information on there. When I saw myself putting that in there, I said, you know what, I should just actually make that an example of how not to make a slide. And then I thought, well, I should also give you a link to Patrick Winston's talk. So check it out if you have time. It's very useful. And I still struggle to meet his standards, as we can see. So anyway, let's move now to some direct space weather phenomenon due to the structures we've just looked at. So we've just looked at the magnetosphere, the magnetic field structure of the Earth, and how it interacts with the interplanetary environment. We've just looked at the upper atmosphere and how that's kind of driven and changes over time. But that we didn't really talk about some of the direct space weather phenomenon linked to those dynamics. So we're going to talk first about background EUV and flare X-ray irradiance. And again, this is not really big storming, but it primes the system for larger storms, geomagnetic storms. We'll also talk about solar wind high-speed streams and co-rotating interaction regions, which we introduced in the last lecture. And again, these don't cause extreme storms, they cause minor to strong storms, but they are worth examining. It's worth examining those phenomena to see some of the things that can happen from a minor to a strong storm. Next week, as I mentioned, we're going to talk more about the solar magnetic eruption effects, coronal mass ejection collisions with the Earth, and solar energetic particle events in particular. And these cause anything from minor to extreme geomagnetic storms and their effects. So that's next week. Right now, we're going to go to just talk about the solar EUV and X-ray irradiance. And this is a plot which shows, again, as a function of time. So these are years on the bottom going all the way back to 1975. The input to the ionospheric thermospheric system from the sun and what the relative power is of those inputs. And as you can see here, energetic particles shown in blue are not very powerful. They have little spikes occurring when there's SEPs, but they're not very overall powerful in terms of what they input into the ITM system. The red is geomagnetic storm input due to heating of those electrical currents in the magnetosphere, and they're pretty powerful. But the most powerful thing, the the most powerful input to the MIT, I should say, system is actually the EUV irradiance from the sun. And you can see it waxing and waning with the solar cycles here. And so on a day-to-day basis, the EUV irradiance of the sun is what really powers the MIT system. It ionizes the ionosphere. It causes the heating and the various dynamics that we see on the day-night transitions. But when you add it all up, you get the black. So that's the total of the blue, the red, and the gold. And what's obviously here jumping out is these very large spikes. Now, what are those? Those are geomagnetic storms. So it's one of the deceptive things about this plot is that the red spikes actually go far above the gold spikes and go into these regions. And so overall, the solar EUV flux as it waxes and wanes with the cycle is sort of the daily climate, if you will, driver of the ionosphere system. But the big driver are the geomagnetic storm events. And those are what really cause these large power inputs to the system. But when we do get an eruption on the sun and we get a flare accompanying it, that sudden influx of very much larger flux of X-rays and EUV will ionize the ionosphere and cause radio communication absorption, essentially. So you'll get a very much higher maximum frequency, and lower frequencies will not reflect from the ionosphere as expected. And what this movie is showing, when you saw the big red oval in the middle there, that's the subsolar point during an X 1.7 flare, causing absorption of everything up to about 20 megahertz, and especially down below 20 megahertz. We play it again. You can see from 15 below in megahertz, sort of the high frequency range, which ham radio operators will use, airlines will use occasionally, is suddenly being absorbed by this very much higher density in the D region of the ionosphere. So that is a direct space weather impact of solar flare X-ray input into the ionosphere. This is a scale of X-ray flare radio interference put out by the Space Weather Prediction Center. It's basically based on the physical measure of X-ray irradiance from the GOES satellites. But for the purposes of dealing with radio communications customers, SWPC labels these events from R1 to R5, rather than calling it an M1 flare, an M5 flare, an X1 flare, X10, et cetera. So you can see R1 to R4 events are not that uncommon. R1 to R3 are actually more common. And R5 events are pretty rare. We don't usually get many flares above X20 in magnitude, but they do occur. Anyway, that's good. It's something you have to know about. So when a space weather person says there's been an R4 event, you know, what are they talking about? They're talking about an X-ray flare in the X10 range. And you can see some of the effects here are also provided. This is available from the SWPC website if you want more information. Okay, and we talked last week also about the fact that when you do get a large eruption on the sun, you'll get sometimes very large radio bursts, or reasons we don't quite understand. Some flares will be more radio intensive than others. This is the event that was talked about in the paper for this week, the 1967 extreme solar radio burst. The flare itself was pretty big. You can see it was a white light flare seen here. It was also a giant H alpha flare. Back in '67, they didn't have the X-ray satellites up, so it wasn't X-ray classified, but they think it was probably an X20-ish. And this had a tremendous, whoops, sorry, just moving the mouse there. This had a tremendous radio burst, which actually jammed the over-the-horizon radars of the ballistic missile early warning system and caused a lot of consternation. It was only because of the very quick reaction of some space weather savvy people in the Air Force that there wasn't a scramble of jets reacting to what they thought was initially a jamming of the radars preceding a Russian attack coming over the North Pole. So that's an example of a direct technological impact that was pretty scary back in 1967. We also talked, I think I showed this last time, there was also a recent solar radio burst, which directly impacted air traffic control radars. So again, flares don't really damage anything, but they can really interfere with things, at least for the hour or two that they're peaking in X-rays and EUV. So let's move on to talking about geomagnetic storms from solar wind in particular. We're not going to get into CMEs, as mentioned, until next week. But if you look at the solar wind high-speed stream and CIRs, geomagnetic storming is what we saw earlier, the magnetic field of the magnetosphere just being buffeted around by the solar wind's magnetic field itself. And these two plots just point out that in quiet times, you can see variations in the magnetic field, and there'll even be little wiggles, but it's only on the scale of about 10 nanotesla. This is a 27,000 or 20,000 nanotesla scale. The horizontal field taken here in Boulder, and you can see quiet time variations are 10 nanotesla. This is a storm. This is the St. Patrick's Day storm from 2015, and you can see here we're talking about sudden variations of 1,000 nanotesla, roughly. So this is what a geomagnetic storm looks like when you're just looking at your ground-based magnetometer and saying, what's going on with the Earth's magnetic field? This was really how they discovered geomagnetic storms back in the 19th century. And they noticed that these storms were occurring in sequence with the solar cycle. So it was the first hint that the sun was somehow linking to the Earth and causing geomagnetic storms. It took another 100 years before they figured out it was actually CMEs causing this, but that's a whole nother story. So again, looking back on this, what we're looking at when we see those plots is the ground-based magnetic field measured underneath this kind of variation. And this model itself doesn't really capture that ground-based variation very well. You don't get a lot of resolution down here around the Earth, but all of that is what's causing this sort of variation through time. And it's important to learn the different categorizations of geomagnetic activity indices. We talk about KP, which is sort of a strange logarithmic by thirds scale developed long ago in Germany. AP is a linear scale derived from KP. And each of these has its own cadences. DST is a particularly useful one, in my opinion, because it has units of nanotesla. And it's really just a plot of the horizontal field averaged from a bunch of stations near the equator. So you get to see these large changes in the horizontal field during a geomagnetic storm triggering. I won't go into too many details. Again, SWPSE has their own scale based on KP, but they use the G designation for geomagnetic storm from 1 to 5. You can read this later and see some of the effects. And this shows a solar wind, a CIR actually incoming and causing one of these G2 level storms or KP6 level storms. Up at the top here is the solar eruptions, little tiny B flares going on, but nothing in particular. But here comes the solar wind measured at L1, and you can see a very sudden density shock followed by a high-speed stream. So a classic CIR impacting the Earth, causing a G2 storm. This is the solar wind, KP, the average of a whole bunch of stations measuring the magnetic field on the Earth. And here's a specific station at Barrow, Alaska, showing its horizontal field all of a sudden going kind of nuts. Not a big one, because this is, again, solar wind. Solar wind CIRs are going to cause, in this case, a G2 storm. It's not going to get up to that G4, G5 level where things get really hairy. Again, we'll talk about that next week. And then this was the aurora caused by, not exactly sure it was that CIR, but this is definitely the CIR level aurora that you'll get. A G2 level storm will cause these nice green arcs. They'll be fairly confined, not too dramatic, but still very beautiful to see. Now, how frequent are these? Geomagnetic storm sources from CMEs are more common than the coronal hole and CIR storms, but about 11% of geomagnetic storms in the sort of the strong to moderate category are caused by CIRs. Most of them are caused by CMEs. So most high-speed streams and CIR storms are down in this G1 to G3 level. Sometimes they'll get to G4. And very quickly, we'll talk about one of the major geomagnetic storm impacts on technology on the ground, which may seem surprising that something in space can get all the way to the ground. But what's happening here is the creation of what we call geomagnetically induced currents in the electric power grid. And how is this happening? Well, what's happening is, again, you have to think back to those magnetospheric currents that are generated by the changing magnetic field as the solar wind or the CMEs buffet the magnetic field. Those giant currents, which are thousands of amps up in the ionosphere, induce magnetic fields by Ampere's induction law. Curl B is equal to mu J. So we've got a big J here, a big current in the ionosphere, inducing a curled magnetic field. That magnetic field is actually propagated all the way down into the ground system here where there are power lines. Well, what's going on? The physics behind the induction is kind of interesting. This has to do with Faraday's induction law, where, as we know, if you have a change in magnetic flux through a loop in time, you induce an electric field around that loop. Well, what's the loop? The loop is actually the power grid shown here, grounded into the earth. So this is a power line going from A to B, grounded into the earth, which is itself a conductor. So suddenly you've got this large, essential virtual loop. This is the magnetic field vector going into the page. The magnetic field drops off as you go into the earth, but it's still non-zero, especially near the surface. So essentially integrating over this large loop, that field induced by those ionic currents are changing constantly due to the current fluctuations in the ionosphere and inducing large voltages in the power line itself. These can be up to sort of 1 to 5 volts per kilometer in a minor storm like we saw from the CIR, but they can get up above 10 volts per kilometer in extreme storms. And you think, oh, 10 volts, what's that? Well, the problem that comes is these L values get up to hundreds of kilometers in some cases, especially for high tension, high voltage transmission lines going from substations and power stations. So suddenly, if you've got a 500 kilometer power line, for instance, and you're inducing 10 volts per kilometer, you've got a 5,000 volt induction into your system. It's also a DC induction on an AC designed system. So the power grid is not designed to have DC voltages come through it like that. And it can, as we'll see in our next week's lecture, induce some real problems at times. And finally, we'll talk about another effect of these currents. As these giant currents are going through the magnetosphere and down into the ionosphere, they're actually heating it up. So this is a plot on the right of the density of the thermosphere as a function of time during a geomagnetic storm. And you can see in the quiet period, the density profile is down more towards the left, but as things heat up, all of the species increase in density for a given altitude. And this joule heating of the thermosphere is what is causing, well, I'll get to the technological effects in a minute. Let's first just talk about a specific example. This is again, the St. Patrick's Day storm in 2015. This is the density over the density of the quiet, normalized by the quiet average density over a series of orbits. Each line here is an orbit of the GRACE satellite at 400 kilometers. So pretty low Earth orbit. This is the plasma density. So the neutral and plasma densities vary. You can see the plasma density varies as you go over the poles. Neutral density doesn't change much when things are quiet. Then when a geomagnetic storm comes along, suddenly you've got this heating of the atmosphere, and these are the densities you get over the same orbits. Very much higher densities, up to a factor of 8 in this G4 storm. And the plasma densities as well, equatorial plasma densities suddenly get very much higher. So what happens when a plasma density or neutral density gets high over your orbital altitude? Well, you get you get drag on the satellite itself. Satellites in low Earth orbit are actually flying through the atmosphere. And when that atmosphere swells up and becomes more dense, you get drag. And you can see that from these low Earth orbiting satellite traces. These are traces over time of the GRACE satellite, CHAMP satellite. And the reason they're going down over time is because they don't have a lot of thrust on board. Here you can see where they do have some thrusting maneuvers to raise their orbits again, but it's really futile. When you're below about 500 kilometers, you will eventually re-enter. And when you're like Gochi down below 300, you re-enter very quickly. even though they had a lot of thrusting going on, they still were able to only orbit for about 3 years below 300. So satellite drag is a real issue when you talk about low Earth orbiting satellites. This is another trace of a particular satellite that didn't have a low Earth orbit, it had an eccentric orbit. Apogee was way out at 3 RE, but when it went down into its perigee in low Earth orbit, over time, the drag in the LEO perigee dragged the satellite over 2 years from a largely elliptical orbit down into a circular orbit, and then finally into re-entry. So again, what's going on here? The satellite is being decelerated by the changing and the increasing density and its own essentially drag coefficient of the satellite, depending on how the satellite is oriented, what sort of solar panels it has, in the ram direction, things like that. But essentially, that's just a straightforward drag equation like you'd see for an airplane occurring in low Earth orbit satellites. So that's it. I think we have a couple minutes for questions. Next week is another Dolores Knit paper, this one about extreme space weather events. Last week's was kind of an extreme event as well, the 1967 event, but I thought it was a nice kind of paper to show you a lot of different effects of a space weather event on different types of technology. It's also historically interesting. This one is comparing various events that occurred over time and the ways to look at extreme events, which we'll talk about in next week's lecture. So any questions?